Black holes are among the most perplexing and strange phenomena in the universe. They remain the focus of intense examination and interest among experts in space, astronomers and physicists alike. Defined by their monstrous gravitational pull and the complete lack of illumination, black holes emit nothing. They are a limit that cannot be exceeded. The established rules of physical science no longer apply, as Albert Einstein first hypothesized in 1916. Black holes, a direct result of his theory of general relativity, were only theoretical until technological advancements allowed for their indirect detection during the 20th century. The pivotal moment occurred during the 1960s, when researchers studying the Cygnus constellation accidentally discovered an unusual celestial object, a brilliant blue star emitting high-energy X-rays. This star's orbit around an invisible partner defied conventional explanations until it was made clear that it was in a gravitational relationship with a massive black hole, Cygnus X1. The discovery of Cygnus X1 provided clear evidence that black holes exist and signaled the start of a new era of investigation into these cosmic enigmas. Cygnus X1, which is approximately 6,000 light-years from Earth, has staggering properties. It is incredibly dense and exerts a gravitational force so intense that not even light can escape its grasp. This defining feature earned it the name black hole, holding the essence of these enigmatic objects. Subsequent research has uncovered a variety of black holes dispersed across the universe, with estimates suggesting that the Milky Way alone may harbor more than 100 million black holes. Despite their elusive nature, which makes direct detection challenging, astronomers have identified numerous candidates in our galaxy, ranging from stellar mass black holes, formed from the remnants of enormous stars, to supermassive black holes located at the centers of galaxies. The gravitational influence of black holes extends far beyond their immediate vicinity, shaping cosmic structures and impacting the fate of surrounding matter. Objects that venture too close to a black hole face a fate determined by its immense gravitational pressure. They are inevitably drawn to the event horizon, the final boundary, where they are subjected to powerful tidal forces and eventually consumed by the singularity at the black hole's core. This catastrophic phenomenon, known as extreme spaghettification, is a manifestation of overwhelming gravity. As an object approaches the event horizon, the gravitational gradient along its length stretches it to an extreme, twisting it into a filament-like shape resembling strands of spaghetti. The forces overwhelm the internal bonds holding the object together, causing it to disintegrate into a stream of matter that eventually merges with the singularity. Despite their allure as laboratories for pushing the limits of physics, black holes remain shrouded in mystery. The search for the truth continues, driven by a desire to comprehend the fundamental characteristics of spacetime and gravity itself. In the vastness of the universe, black holes stand as silent sentinels, beckoning humanity to explore the depths of the unknown and expand the boundaries of knowledge. Despite the tremendous distance, approximately 1,500 light-years, separating us from the nearest known black hole, questions and concerns about their potential effects persist. In 2021, researchers achieved a monumental breakthrough by capturing the first clear image of a black hole, specifically M87, located at the center of the Messier 87 galaxy. This remarkable achievement provided critical insights into the nature of black holes. The visual data revealed that black holes possess complex layers, challenging the traditional view of them as solitary entities of pure nothingness. Through meticulous analysis and image stitching, scientists identified three distinct layers within a black hole. 1. The event horizon, the outermost layer, marking the point of no return. After crossing this limit, escape is impossible due to the immense gravitational pull. 2. The photon sphere, the second layer, where light orbits the black hole in perpetual captivity. Photons that enter this region become trapped forever. 3. The singularity, the third and final layer at the core, where the known laws of physics break down. Here, conventional understanding fails, plunging researchers into a realm of profound uncertainty and theoretical speculation. The complexity of black holes and their immense variation pose significant obstacles to our understanding. While the three-layer structure may be shared, each black hole exhibits unique characteristics and behavior, defying simple classification. Traditional methods of scientific research are insufficient. Innovative approaches are necessary to study these enormous cosmic entities. Indirect observation remains the primary method of investigation, as direct study is rendered impossible by the immense gravitational barriers. Attempts to send probes into black holes would result in their destruction, rendered insignificant by the ferocious forces at play. Nevertheless, researchers persist in their quest to decode the secrets of these cosmic giants. Various theories, from stellar collapse to cosmic dynamics, offer intriguing clues about their origins and behavior. Notably, NASA's investigation of M87's core revealed compelling evidence of a supermassive black hole exerting gravitational influence across vast cosmic distances. Despite the challenges, the pursuit of knowledge continues unabated, driven by humanity's innate curiosity and thirst for understanding. While the enigma of black holes may elude simple explanation, the steadfast dedication to scientific inquiry promises to illuminate the darkest corners of the universe, unraveling profound secrets hidden within. The groundbreaking work of Roy Kerr in 1963 offered a transformative model of rotating black holes, challenging conventional perspectives. Central to Kerr's model was the concept of the ergosphere, a region surrounding a rotating black hole where divergent forces prevent matter from collapsing further inward. This novel domain displayed peculiar deviations from classical physics, hinting at deep mysteries concealed within black holes. However, the most intriguing implication of Kerr's theory was the prediction of an Einstein-Rosen bridge, informally known as a wormhole. This hypothetical structure represents a potential gateway through spacetime, offering a conduit between distant regions of the universe, or even between parallel universes. The concept of wormholes arises from the intricate relationship between reality and Einstein's theory of general relativity. In this framework, existence is woven into a four-dimensional fabric called spacetime. Massive objects warp this fabric, creating gravitational fields that influence the motion of nearby matter. Wormholes theoretically function as shortcuts across this cosmic fabric, connecting distant points in spacetime and potentially enabling rapid travel. Despite the vastness of cosmic distances, wormholes remain purely theoretical. No observational evidence currently supports their existence, and their stability, if they do exist, is highly questionable. Theoretical models suggest that to keep a wormhole open, a form of exotic matter with negative energy density would be required. This kind of matter has yet to be discovered, and its properties challenge even the most advanced understanding of physics. Still, the idea persists because of its profound implications. If wormholes could be stabilized and traversed, they might allow for instantaneous travel across galaxies, or even time travel. Such concepts, once relegated to science fiction, now inspire real scientific discussions and drive advanced research in quantum gravity and string theory. In the ongoing effort to unify general relativity and quantum mechanics, black holes have become critical testing grounds. At their core lies the information paradox, a conflict between quantum mechanics, which insists information cannot be destroyed, and general relativity, which implies that anything swallowed by a black hole, including information, is lost forever. This paradox has sparked debates for decades. Theoretical physicist Stephen Hawking proposed in the 1970s that black holes emit radiation, now known as Hawking radiation, and slowly evaporate over time. However, the fate of the information absorbed by a black hole remains unresolved. Does it escape with the radiation? Is it imprinted on the event horizon? Or does it vanish entirely? Modern theories, such as the holographic principle, suggest that all the information absorbed by a black hole is actually stored on its surface, not inside. This radical idea, supported by research in string theory, proposes that the three-dimensional reality inside a black hole may be an illusion. Everything is encoded on the two-dimensional boundary of the event horizon. Such theories not only reshape our understanding of black holes but also of the entire universe. They imply that our universe itself might be a hologram, a projection of information stored on a distant cosmic surface. In recent years, breakthroughs in computational power, space observation, and quantum theory have reignited interest in exploring these questions. Telescopes like the Event Horizon Telescope, EHT, continue to capture unprecedented images of black hole shadows, while instruments like LIGO detect gravitational waves, ripples in spacetime caused by violent black hole mergers. Each discovery peels back another layer of the cosmic unknown, bringing us closer to understanding these silent, dark giants. And yet, every answer seems to lead to new questions, reminding us that black holes are not just celestial phenomena, but cosmic riddles. They test the limits of human imagination, our technology, and our very understanding of reality. In their silent pull lies a message: the universe still holds secrets far beyond our grasp, waiting patiently in the darkness for curious minds to uncover them. Wormholes' practicality and stability remain subjects of intense speculation, as well as discussion among theoretical physicists. While the presence of wormholes provides tantalizing possibilities for time travel and interstellar travel, significant difficulties and restrictions temper these fantastical dreams. The intrinsic instability of wormholes, in addition to the formidable barriers posed by radiation and quantum forces, casts doubt on their feasibility as viable means of transportation. Moreover, the general relativity theory proposed by Einstein imposes fundamental constraints on the speed of travel throughout spacetime. This suggests that even if stable wormholes existed, they might not facilitate faster-than-light travel. Although faster-than-light travel is an important part of many sci-fi narratives, the allure of wormholes persists as a shining example of scientific curiosity and the investigation of cosmic mysteries. The idea of the wormhole, named after its pioneering scholar, embodies the tantalizing promise of cosmic portals and alternate realities, inviting humanity to ponder the universe's mysteries and contemplate the inconceivable possibilities that lie beyond. The quest for a single theory that unites the seemingly disparate domains of gravity and quantum mechanics has spurred the search for an explanation of everything, a comprehensive framework capable of incorporating all fundamental forces and particles in the universe. At the forefront of this endeavor stands Myoku, a well-known theoretical physicist whose groundbreaking work has helped propel the study of the theory of superstrings. Superstring theory is a significant departure from conventional ideal models, assuming that fundamental particles are not point-like entities but instead microscopic vibrating strings. These strings, similar to those of a musical instrument, resonate at specific frequencies, giving rise to the various particles and forces observed in nature. In this paradigm, the universe becomes akin to a grand symphony, with each particle corresponding to a unique harmonic resonance of fundamental strings. One of the most striking implications of superstring theory lies in its potential to explain mysterious events associated with wormholes, black holes, and other exotic solutions to the equations of Einstein's gravity. As strings traverse the fabric of spacetime, their dynamic motion leads to the formation of gravitational singularities and topological anomalies. However, the elegance of superstring theory masks its inherent complexity, as it necessitates the existence of additional dimensions, beyond the familiar three spatial dimensions and one temporal dimension. These hidden dimensions, invisible to direct observation, present a significant challenge to human intuition. Nevertheless, applied models, such as the analogy of fish inhabiting a two-dimensional lake, offer glimpses into the elusive nature of these higher dimensional realms. The compactification of these extra dimensions, akin to folding a rolled-up piece of paper, makes them difficult to notice on a daily scale. Yet, their influence permeates the very fabric of reality. While the precise nature of these subterranean dimensions remains elusive, their conceptual presence offers a promising explanation for complex structures and anomalies observed throughout the universe. The mathematical foundations of superstring theory have sparked a renaissance in mathematical physics, demonstrating significant connections between dynamic mathematical patterns and physical phenomena. In fact, the search for a theory of everything has become a catalyst for a synthesis of fields that sheds light on the deep interplay between mathematics and the natural sciences. Despite its theoretical elegance and scientific promise, superstring theory remains an untested framework, still awaiting experimental validation. The elusive nature of extra dimensions presents a formidable barrier, relegating the experimental verification of superstring theory to the realm of mathematical speculation. Nevertheless, the audacious vision of superstring theory continues to captivate the minds of enthusiasts and researchers alike, enticing humanity to embark on a journey of intellectual discovery and exploration. As we venture deeper into the known domains of theoretical physics, guided by the illuminating beacon of superstring theory, we confront the mysteries of the universe, poised at the beginning of a new era of understanding and enlightenment. The task of unraveling the secrets of quantum black holes has long perplexed physicists, representing a monumental challenge to our understanding of the fundamental nature of the universe. Despite numerous efforts to tackle this riddle, a live solution has remained beyond our grasp. Physicist Edward Witten, from the Institute for Advanced Study in Princeton, once described superstring theory as 21st-century physics that accidentally fell into the 20th century. However, recent advancements have injected new hope into the quest for understanding quantum black holes. Several groups of physicists have independently reported a significant breakthrough, revealing that string theory could offer a comprehensive solution to the issue, though within the more constrained context of two dimensions, rather than the full 10-dimensional framework set forth by conventional superstring theory. While this represents a promising step forward, the quest for a complete resolution remains ongoing. The complexities of the situation present significant hurdles. Still, the search for a single theory of everything beckons us to probe the deepest recesses of cosmic existence, where the boundaries between reality and theory blur, and the universe's secrets await discovery. The study of black holes carries significant implications for our understanding of the universe, challenging our notions of reality and raising profound questions about the very nature of existence. The interaction between black holes and other astronomical phenomena, such as neutron stars and gamma bursts, reveals the intricate processes at work in the cosmos. These interactions not only offer insights into the life cycles of stars but also illuminate the mechanisms driving some of the universe's most energetic events. As black holes consume matter and collide with other celestial bodies, they generate ripples in the fabric of spacetime, gravitational waves, that have only recently been directly observed, thanks to groundbreaking instruments like LIGO and Virgo. These observations mark a new era in astrophysics, enabling scientists to listen to the universe in ways never before possible. Through the analysis of these gravitational waves, researchers are beginning to decode the hidden language of the cosmos, gaining invaluable knowledge about mass, spin, and the mysterious behavior of matter under extreme conditions. Yet, despite the progress, many questions remain. What happens at the core of a black hole, beyond the event horizon where known physics breaks down? Could information truly be lost forever, as once proposed by Stephen Hawking, or does it somehow persist, hidden in quantum fluctuations or encoded on the surface of the event horizon, as suggested by the holographic principle? These puzzles lie at the heart of modern theoretical physics. Bridging the apparent contradictions between general relativity and quantum mechanics is not just a matter of scientific ambition, it is essential for achieving a complete understanding of the universe. Superstring theory, with its promise of unification, continues to offer tantalizing hints, but a fully consistent and testable model remains elusive. Meanwhile, the broader scientific community explores alternate paths. Loop quantum gravity, causal dynamical triangulations, and other innovative frameworks each propose different ways to reconcile gravity with quantum theory. These competing models, though differing in detail, reflect a shared drive to comprehend the deep architecture of reality. As our mathematical models grow more sophisticated, so too must our observational tools. The future lies not only in chalkboard equations but also in cutting-edge technologies, space telescopes, particle accelerators, quantum computers, that will allow us to probe the finest threads of the cosmic fabric. In the grand tapestry of science, wormholes, black holes, and vibrating strings are not mere abstract constructs. They are symbols of humanity's relentless curiosity, a testament to our refusal to accept ignorance in the face of the unknown. Each breakthrough brings us a step closer to an ultimate truth, one that may reshape our understanding of time, space, and existence itself.